Good morning, everybody. We'll just give it a couple more minutes for a few more people to join, and then we'll get going. Okay, good morning, everybody. We'll kick off now. Welcome to this UKBIC webinar, which looks at controlling air in battery slurries during electrode manufacture. We'll start with just a few little bits of housekeeping. So if you have questions throughout the webinar, please use the Q&A function on Teams. We will address the questions after the presentation, and we'll try and get through as many questions as possible. If you'd like to reach out after the webinar, please use either sales@ukbic.co.uk or info@ukbic.co.uk. If you're watching this live, then you will receive a copy of the white paper to accompany this presentation following the webinar. Otherwise, you can find a copy of the slides, a recording of the presentation, and the white paper on the UKBIC website from today. So I guess a little bit about me. I'm Helen Walker. I am a senior simulation engineer here at UKBIC. So my main role is to develop multi-physics simulations of the manufacturing processes here at UKBIC. Before UKBIC, I was at the Manufacturing Technology Centre, also in Coventry. And my background before that is a PhD in fluid dynamics. I'm also accompanied today by two colleagues, Grant Griffin, who is a quality engineer, and Dr. Andrew Mottram, who is our technical expert for mixing and coating. So at the end, if I'm not the best person to answer your questions, I'll be passing you over to my colleagues. So a little bit about UKBIC. We are the UK's battery manufacturing scale-up facility. We enable customers to scale up from lab scale to giga scale, and we really are the bridge between R&D and industry. We're funded by the Battery Innovation Programme, and that funding comes from the Department for Business and Trade, and it's delivered by Innovate UK. So today's presentation is really about all of the work that we've done over the past couple of years at UKBIC, looking at unwanted air in our battery slurries to achieve defect-free product. It's been a real cross-functional approach with product engineering, manufacturing engineering teams, quality and operations. And these are really all of the findings that we've come to that really make a difference in electrode quality. So today I'll begin with a brief background into wet slurry electrode manufacture for those who perhaps aren't so familiar, and take you through the UKBIC way of coating. I'll talk about how we check for gas in our slurries, and then I'll go through all of those strategies that we've implemented to mitigate air in our slurries, and that includes product design, it includes process optimization, and there's a bit of simulation in there as well. So The first stage in electrode manufacture is mixing. We're mixing conductive materials, active materials, additives, and a solvent to form a slurry. Now, arguably mixing is probably the most important process in electrode manufacture. If you don't get your mixing right, it leads to problems down the line. What we're really after is a homogeneous slurry, free from agglomerates, because if you don't get that right, then it's difficult to coat, and if it's difficult to coat, then you have defects that will cause you problems at calendering, etc. So mixing is very, very important. Traditionally, in battery manufacture, we use a batch mixing process, and this is what we have at UKBIC. We have a large 400-litre IRIC mixer. Batch mixing, the downside for batch mixing is that you can get variability between batches. There are continuous mixing solutions out there, but at UKBIC, we do batch mixing. We have an intensive mixing process. Now, by its nature, mixing is a turbulent process. You can imagine, by its very name, intensive mixing is even more turbulent. And so when you're doing that mix, you're entraining air into your slurry. Now, there are mixers available that allow you to mix under vacuum. These are more costly and they are more complex. At UKBIC, our mixing is not under vacuum. In hindsight, if we were to build this facility from scratch in the future, we might choose to have mixing under vacuum, but we don't, which means that we then have to go through a process of degassing. Also important to note at this stage that the parameters that you use within your mixing procedure can also influence the final viscosity of your slurry. Now, battery slurries are shear thinning. That means that when you apply force to them, the viscosity drops. So just something else to think about, that what you do at mixing can really affect the way your product behaves downstream. Not only is the air that is entrained at mixing a cause for concern, there are other gases that can be generated in a battery slurry. If you have silicon-based anode materials, there is a chance that when you're combining that material with water, that you can generate hydrogen gas. There are a number of steps that can be taken with your material to reduce this risk. One of them is increasing the oxide layer thickness on the outside of your particles. Another option is carbon coating your materials. But at UKBIC, we always take care when we're processing a new material to monitor a trial batch of that material, so we're confident that when we take it to large scale, we don't have any unwanted gases generated. We don't just do this for a small period of time either during mixing. We will take a trial batch and we will monitor it for up to a week afterwards, because we want to make sure that if we've left some slurry on agitation for overnight, say, there's no concerns there. Another thing to remark is that if you're processing pre-lithiated SiOx, there is also another potential reaction that can take place between the lithium and water to produce hydrogen gas. So it's very important that we do that due diligence before we do any large-scale mixing. Okay, so once we have completed a mix at UKBIC, we then transfer that slurry from the mixer into a transfer vessel, which you can see on the right-hand side. It's the silver vessel on the right-hand side in that image. And this is where our degassing takes place. So typically, in the battery industry, slurries are degassed anywhere between about 50 and 200 millibar. Our transfer vessel that you can see here on our industrial scale-up line, we can degas down to about 40 millibar. Now, why is this important? After you mix, we have these tiny, tiny micro bubbles in our slurry. If we were to let them degas at ambient pressure, they would take a very, very long time to rise through the slurry and reach the surface. When we're degassing and we drop the pressure in that vessel, that bubble can very quickly expand. The density of that bubble drops, and so Archimedes' principle, the bubble is able to rise far faster up through the slurry column. As it rises, it's able to expand further, and it expands further, it rises quicker, and the bubbles accelerate towards the surface. Now, if we've been able to degas our slurry successfully, the next thing that we have to do is transfer that slurry to the coating head, whether that's slot die coating, which we do at UKBIC, comma bar coating, knife coating, curtain coating. Depending on the setup of the equipment, that involves moving the slurry through pumps, pipes, filters, valves, and each component that you have increases the risk of air making its way into the system. So it's not just that you've entrained air at mixing, it's that actually you could be unwantingly or unwittingly introducing air at slurry delivery. So once you've delivered your slurry to the coating head, if you still have air in your slurry or you've entrained air in your slurry in your slurry delivery system, bubbles can then become problematic for the coating process itself. So bubbles will destabilize what we call the coating bead between the slot die or whichever mechanism that you're using and the substrate, and this will lead to uneven coatings. If you are trying to skip coat your slurry for cylindrical cells, this becomes even more problematic. When you're skip coating, you need really good control over the pressure in your system to be able to achieve that skip. If you've got air in your system, it acts like a spring, and so you're not going to get really nice, clear, defined lines in your leading and trailing edges of your skip patches. So, yeah, very, very important if you're wanting to achieve really nice, crisp skip coating. So how do the bubbles manifest in the product itself? So at UKBIC, we categorize defects under two names, really. So when the slurry exits the slot die, translates onto the foil, the bubbles will burst. And we say they either form pinholes, which we define as a defect which penetrates all the way through to the foil, or a fisheye, which is a concave circular shaped defect that doesn't quite penetrate to the foil. And these have a terrible effect for your batteries. So, you don't have a homogeneous, uniform layer of active material anymore. So you're going to have hot spots, you're going to have over potentials, and ultimately that will reduce your energy density of your cell. And over repeated cycles, it's going to result in, shorter life cycle of your cell. And in really, really bad cases, if you've got lots of current collector exposed, you've got that risk of internal shorts. So we really want to avoid these defects. At UKBIC, we have a in-core vision system which monitors our defects. Now, the way that you set up your vision system will be very specific to you. It depends on the level of defect in which you are willing to tolerate in your cell. And that, you will have to define that from your own trials at the cell level. What is important is that your system is calibrated on your material and that you've set that threshold correctly. You want to be spotting the defects that are going to affect your cell performance. You don't want to be picking up small defects or just noise. So yes, it's very, very important that we calibrate our vision systems correctly. So I've talked about the wet slurry casting technique at UKBIC. So I'll now talk about how we detect or quantify the air that's in our slurry. So once we have degassed a slurry, we perform what we call a degas check. We take a sample of that slurry, we decant it into a small vial, and we place it into a vacuum oven in our lab. Trying to be very, very careful, again, not to reintroduce any air into the sample. And then we, in that vacuum oven, we drop the pressure, and what we're monitoring is for bubbling of the slurry. We have learned that it's probably best to repeat the sample. So you'll see in the image on the right hand side or the video on the right hand side, we have 3 slots for 3 samples in our vac oven. This is just in case there's been some error with the handling. If you've got 3 samples, you're going to get a much more reliable indication of if there's air in your slurry. And so what we're really looking for is, are there small bubbles that are appearing on the surface? If there are, that indicates that you do have some air in your slurry. If we get significant rise in the height of the slurry column, we know that there's significant trapped air in our slurry. But there's a word of warning here. So at different pressures, different solvents will boil at different temperatures. And so we have to be very, very careful that both when we are degassing and when we are performing our degas check, that we are not starting to boil off our solvent. Now, there's an equation that we can use that can help us calculate this, and this is this Clausius-Clapeyron equation. And if you know for any solvent, it's vapor pressure and at a temperature, then you can use two other constants, so the gas constant and the enthalpy of vaporization, to work out its boiling point at a different temperature. Now, this is particularly important for water-based solvents. So on the right-hand side, I've plotted a graph where you can see how the boiling point of both water and NMP changes with pressure. I mentioned earlier the degas pressures that we work to on our ISL line, about 40 millibar. As you get to those low pressures, the boiling point of both NMP and water reduces. Water in particular, as you get to those low pressure, the boiling point of water starts to get towards, 40, 30, maybe high 20 degrees. And so we're really, really at risk of boiling off our solvent. NMP, you can see the risk is slightly less. So I guess the point here is twofold. If you're degassing at a low pressure, and you're leaving that slurry for a significant amount of time, there's a very good chance that you're boiling off your solvent, your solids is going to increase, and your density will therefore increase, and your viscosity will increase. So but it might be that your slurry then becomes, out of specification. In your degas check, what this could lead to is misleading results, because what you might be observing is, oh, there's some residual area in our slurry, we need to degas it longer. Actually, you could just be boiling off your solvent. So this check is very important to know exactly what your boiling point of your solvent is at the pressure that you're working at. Now, at UKBIC, I mentioned our industrial scale-up line degas or transfer vessel where we degas can go down to 40 millibar. Our new flexible pilot line has smaller transfer vessels, and in those transfer vessels, we can take our slurry down to a lower pressure. So it becomes increasingly important there that we're doing these checks. So how do we know how long to degas our slurry for? Well, there are two equations really that we can use to model the degassing of a bubble out of a fluid. On your screen here, you'll see the Rayleigh-Plesset equation, and this equation governs the growth of a bubble in a slurry under changing pressure. So we imagine that we've whipped a bubble into our slurry during mixing, and then we can model how, as the pressure drops in our vessel, the bubble expands. And then as it expands, we can use another equation, which is Stokes' law, to model how the bubble moves up through that fluid column, and it expands and it accelerates, expands, accelerates. And what we've been able to do at UKBIC is implement this model and package it into an executable file for our process engineers to use. What this model also tells us is all of those levers that we can pull to try and reduce degas time if need be. It allows us to understand which parameters are really affecting how long it takes to degas our slurry. All of those things listed on the right-hand side are very important. So as our vessel is very important. If we're degassing in a vessel where you've put a volume of slurry and it's got a small column height, you're going to be able to get those bubbles out quicker. If your vessel has a narrow radius and you've got a large fluid height, it's going to take longer to degas. So we're quite aware at UKBIC of choosing the right vessel for degassing and how that will affect degas time. But the other two biggies that really come out are the density. So the more dense your slurry is, the quicker a bubble is going to rise, Archimedes' principle, and the viscosity, because that viscosity, I mentioned Stokes' law earlier, will affect how much viscous resistance there is to a bubble moving up through the slurry column. And what we found at UKBIC is, viscosity and density, you can't change one without the other. If you decrease your density, you will decrease your viscosity. And so it's a trade-off between those, the buoyancy forces and the viscous forces. And we found that, you know, if we reduce our density or our solid content by 1 or 2%, we can quite significantly influence the viscosity, and actually degassing becomes easier. And so it will depend upon, our customers and what people are willing to change with their formulation. But formulation can be amended to improve degassing. And we can look at other things as well, like dispersing agents or changing binders. But UKBIC, we've done limited work in that area. So another thing that we've done at UKBIC to improve degassing time is by changing the style of the agitator in that transfer vessel. When we're degassing, we're slowly agitating this slurry all the time. Some designs of agitator, well, all agitators will induce a circumferential flow. Some designs of agitator will be better at inducing vertical currents of flow. Now, if you can induce vertical currents of flow, you're not only relying on buoyancy to degas your slurry, but you're also convecting those bubbles up to the surface where they can pop. So we have moved from the design on the left-hand side, which we call the cups style agitator, to a helical design on the right. And we've noticed superior degassing performance by making that change. And we can explain this by some computational fluid dynamics modeling that we've done. So we have modeled the agitation of a slurry at with the cups and the helical design at the same rotation rate. And we find that in the top image, you'll see the helical design induces far more vertical flow. And then in the bottom image, you will see the shear rate in the vessel is much higher with the helical design. Now, battery slurries, I mentioned earlier, are shear thinning. So as you apply a force to them, the viscosity drops. And this is advantageous for degassing, because if we're shearing that slurry more, its viscosity is decreasing. And so those bubbles can rise more freely. So actually the change in agitator design works twofold. So I mentioned slurry delivery system being important. So as part of quite significant engineering upgrades that we had on our line last year, we changed our slurry delivery system. It not only was a much more streamlined system, the new system that we have, but it also improved our capability in other areas. But what it meant was that we moved from a system which had 45 connections to 17 connections. So if you think about it, that's, when we're disassembling and reassembling to clean and maintain the equipment, it's less seals that have to be, inspected and reassembled. Far fewer points for failure. The other difference between the old and new system that we have at UKBIC is that the previous system had a rope seal type pump. Now, this works by allowing some leakage of the fluid, and that's what lubricates the pump. Now, wherever you are allowing intentionally some leakage out of your system, there's always the risk that air can get in. We've now moved to a mechanical seal pump. Now, if you've successfully managed to transport your slurry to the coating head, there's one final area where you can risk air entrainment, and this is right under your coating head. So I mentioned earlier at UKBIC, we primarily do slot die coating. So slot die coating is a pre-metered process. So you're feeding slurry into your slot die. The roller is or the substrate is moving underneath that slot die and translating that slurry away. In between your slot die and your substrate, there's a very fine balance of forces going on. You've got inertia, gravity, surface tension of the slurry, and viscous forces. And the stability of that process depends on getting a really fine balance between these things. As mentioned, these are shear thinning slurries. This is not simple physics. It's all quite complicated. Excuse me. So what we can do is we can model this process with computational fluid dynamics models, so that before we go to coat a slurry, we know how to set up our process to reduce the risk of air entrainment. So what you're seeing on the right hand side here is slurry is coming down that top channel in the slot die internally. It's able to then translate onto the foil, and the roller is moving to the right. And we model a number of scenarios, and what we're modeling here is different on-coat positions or different distances between the substrate and the slot die. Now, in case A, that slot die is too close to the substrate, and so you're getting slurry come out of the upstream area of the meniscus, and you'll get dripping. As you increase that on-coat position, increase the distance between the foil and the slot die, you get to a point where you get your meniscus balanced in a preferred place. So in figure C, you see the meniscus is pinned really nicely on the upstream slot die lip, and this is what we're after. All our force is nicely balanced, and we don't have any risk of air entrainment. What we don't want is case D, where that on-coat position is too big. Your meniscus or your coating bead is getting dangerously close to your slot die exit, and that's when you risk pulling air into your slurry. Now, these computational fluid dynamics models they're big. They require specialist knowledge and training, and a lot of compute power, and they can take hours to run. So as an alternative to this at UKBIC, we have another tool, which is an analytical tool, which is just the implementation of a model taken from a book. And for those of you who've seen stability windows before, this will look familiar. But what we can do in this tool is we can pull in the rheology, the surface tension, and the geometrical parameters that we're interested in. We can run this analytical model that was developed by Schmidt, and it will tell us for those parameters whether we risk entraining air. Now, again, like I mentioned with the degas model, this can be packaged up into an executable file or an app. It can be given to process engineers who can use it on the line rather than relying on simulation engineers to run, really computationally expensive models. And what we really want here is so that when the process engineers are coating a new slurry, their initial parameters that they're starting at, we're getting started straight away, and we're not wasting material or time on the line trying to dial in, as we would call it. So I guess really we just want to conclude that understanding degassing is really, really important. Understanding what levers that you can pull or you're willing to pull to ensure that you are efficiently able to get those bubbles out of your slurry is really, really important. And it might be that actually you are willing to modify your formulation to do so. Equipment design is important, streamlining the equipment so you've got as few points of failure as possible is critical. And then understanding finally that coating process towards the end is that sort of last step in ensuring that you don't get defects in your material. And all of these things together that we've done over the past probably 2 years have really meant that the yields that we get at UKBIC are significantly improved. So everything that I've discussed in this webinar is contained and more in the white paper that will be released today. If you're watching live, you'll get a copy of this white paper sent to you by email, and if you're watching as a recording, then you'll need to go to the UKBIC website and download it. I'll now open up to questions and introduce again my colleagues Grant and Andrew, who are here to answer any questions that you have. So just bear with me a moment. Okay, do we have any technical questions that we would like to ask anybody? Okay, right, so we've got one from Charles. Can magnetic fields traps for contamination be an influence on air entrapment? We are changing from normal to electromagnets and wonder if you had any thoughts. I'm going to defer this question to my colleague, Andrew Mottram, I think.
Question.
I'll try again. We haven't seen any correlation between our magnetic trap and air entrapment. I don't quite see how magnetic fields in themselves would cause air entrainment. It's not something we've looked at.
Does that answer your question, Charles, or is there anything else you'd like to follow up with? Okay, so we've got a question that has been asked previously. And so the question is, are simulation models available for customer use or license? So this is something that we are working on. Those computationally expensive CFD models require specialist software, specialist licenses, but those tools that we've developed, like the degas model, the coating stability model, that are written in open source code, essentially, we are looking to host them somewhere and provide access to them. So that, yeah, that is something that we're working on. Okay, so we've got, what is the white thing in the fisheye defect in slide 12? One moment, I'll just go back. Okay, so we've just circled the defect with a chalk. I'll let Grant talk on this one.
Yeah, so that's just there is some white China graph pens, I believe they're called, or pencils. They are just an easy way to identify or mark up electrode material, which we use just to make it clear on that black or grey background that this is what you're looking at. So that's just what you're seeing in that picture. I assume that's what you mean. If that's not the case, please just stick another note in chat.
Next question, okay, we have, so does this optimum slot die to wet coat thickness also correspond to the minimum edge bead size, or is another variable needed to minimize this? Okay, so I think I can answer this. So in the high fidelity CFD model, those models are 3D. So we can not only look at speed stability, but we are also able to predict high edges. Now, as well as surface tension, we also need the contact angle of the slurry with the substrate in that model. And as you can imagine, the high edge prediction is very, very dependent on that contact angle measurement. Yeah, and we are able to measure that in the UKBIC lab. So we have reliable inputs for our CFD model. Is there anything that you'd add to that, Andrew?
I guess the coating window is part of the model, and then edge effects, how a coating window affects the edge effects, is another part, which isn't, it needs a high simulation model at the moment, but it's something we're actively progressing and investigating, and we recently got the inline capability to quantify in a few more details. So I'd hope to have a bigger update in 6 months.
Okay, we have a question. You talked about defects arising from slurry coating could impact the electrode performance. What are the size of these defects range? I think I'm going to pose that question to Grant.
Yeah, I mean, you can get a very large range of defects in your electrode material once it's coated, depending on the size of the bubbles that are inside the slurry or generated through the other means. It can range quite a bit, but the effect that has on your electrode performance will probably vary, but it will be specific to your chemistry, cell performance, and the size that you have on your electrode. So it's one of those aspects which needs testing in a particular situation to understand how it will affect your performance. Smaller defects logically will have less of an impact than larger defects, but it does need some particular testing. I think, Andrew, do you want to add anything to that?
The only thing that came to mind is that the size of the defect, the air bubble, can also be linked to the size of any filters that pass through, and then the size of the filters relative to the size of the wet film thickness can also be a sign of how the defect manifests on the coating itself. So because we tend to use 50 to 75 micron filters, often the defects tend to be in that ballpark range.
I was just going to add on to that. Some of the other aspects that Helen's talked about around different mechanisms to generate defects on your surface can present as different size ranges. So, for example, air entrapment through your slot die meniscus could introduce quite small defect sizes, whereas large bubbles inside your slurry might present as bigger ones that, once they've gone through the filter, get broken down into smaller ones. So it does depend on where you believe the defects, the area is coming from.
Okay, we have a question. How are analytical models for coating process optimization being trained or validated? Do you have any use cases? So the CFD model, there is a case study on our website. So as I mentioned, the CFD model is a 3D model, and it predicts the stability of the meniscus, which is very hard to validate because you're talking right under a slot die, but it also predicts coat uniformity across the web. So on the case study that's on our website, we present the output of the simulation, which gives the coat uniformity across the web, and then we overlay some line side measurements. Very recently, we have upgraded our inline measurement systems at UKBIC to a Scantech system. And so we're able to better validate the CFD model because we have very high fidelity cross-web profiles. So yeah, it's through that cross-web profiles. Are we predicting those high edges and coat uniformity accurately? Okay, another question from Scott. From a cathode active material side, do you see differences in gassing volumes depending on CAM chemistry, NMC versus LFP as an example? I think I'll send that one to Andrew.
From a electrode manufacturing perspective, we haven't seen huge differences between LFP and NMC. The different particle size range on certain LFPs can make degassing a bit more complicated. We have seen bigger differences during formation, aging and testing, but not so much in terms of electrode.
I'll give it 1 more minute, but I think questions have slowed down. Okay. Yeah, we could do 1 more pre-submitted question. Which one do you think, Grant, would be most relevant?
Which of these improvements / models made the most difference to defect reduction?
Okay. Yeah, so as I said, we made quite a few improvements to the way we did things at UKBIC in one go. We had the line upgrades, we improved the slurry delivery system. We started using models a lot more frequently. So for us, it is very, very hard to decouple which had the most impact. Is there anything that you'd add on that, Grant?
I think it depends on the type of defect that you're seeing and where you believe it's coming from, which will have a bigger impact. Like we said before, or like Helen's explained in the webinar, there is some aspects that are important to identify at the offset so that you understand potentially where the gas generation is coming from, and making sure that you've captured all the easy identifiable bases to make sure that you're not missing anything from that. So there is bigger impacts depending on where the gas generation comes from. So it's a bit of a complicated question, but yeah, there's plenty of steps to go through.
Okay then, so I think we will wrap it up there. But yeah, just a reminder, if you're on this webinar now, you'll receive an email with the white paper attached. And if you're watching it as a recording, then you'll find the slides, the recording of this webinar, which we'll be watching, and the white paper on our website. So thank you ever so much for joining us today. And yeah, if there are any last questions, then please contact one of those email addresses, and the team will put you in touch with the right person at UKBIC.